This is phase 1, lecture 4. So we ended last time with that slightly more convenient notation of factorial. Let's try and remember that. Short way to write. We had, I think, 9 times 8 times 7 times 6, all the way down to 1. Short way to write that is 9 with an exclamation mark. And I read this as 9 factorial. So it's just a way in my calculations, in my solutions for counting things, a product like this is going to come up, where I start with a number and it's all the way down to 1. I just want it more convenient, a shorter way of writing that, and this exclamation mark, this factorial, is going to allow me to do that. So it's just for convenience. So I want to get used to this notation, and I want to use this so that I can have things more concisely written. So where did this, the previous example gave me that 9 factorial, and we looked at how many ways can I arrange 9 people in a row. So this was the number of ways to arrange 9 people in a row. I wanted to count the batting orders, and essentially I have to line up 9 people. How many ways can I do that? Well, the first position had 9 choices, then the second position had 8 choices, 7, 6, all the way down to the last position. This is my convenient way of writing it, and I'm counting the number of ways to arrange 9 people in a row. So things like that is what we're going to look at today. So we call this permutation. Permutation is simply an arrangement of objects. In a row. I'm not just arranging them anyway, I'm lining them up. I'm arranging them in a row. So let's look at number 1. Example number 1. The class in probability theory consists of 6 men and 4 women. A test is conducted, and the students are ranked according to their performance. Assuming that no 2 students obtain the same score, how many different rankings are possible? So often I have to, I'm trying to answer a question, but I'm sort of transferring that to something equivalent. And in this case, a ranking, let's say it here, I guess, a ranking corresponds to an arrangement. In a row. So for every way I can arrange the 10 people in a row, that gives me a ranking, let's say from left to right. So if I'm trying to count the number of ways that I can rank these people, I'm really just counting the number of ways that I can arrange them in a row. These things are equivalent. So let's do it over here. So how many ways can I arrange 10 people in a row? That is exactly what this or let's say here number of arrangements, I guess is also acceptable. Number of arrangements is 10 factorial. That's exactly what this factorial thing represents. Now, if you really want to hold on to it, you can write 10 times 9 times 8 times 7 all the way to 1. Because I have 10 choices for the first position, 9 choices for the second position, and so on down the line until the last position. But I want to start getting used to this. Factorial. It's the same thing. So how many ways can I arrange 10 people, 10 things? 10 factorial ways. Any questions on this factorial exclamation mark business? This is in a sense the method that allows us to express and count different things. And I wanted to do that in a nice, short, convenient form, and this is the notation that I'll use. In B, I'm trying to rank the people again, but I'm looking for different rankings if the men are ranked just among themselves and the women just among themselves. So I can break this up into 2 steps. I know what I'm looking for at the end. Step 1 could be, let's just arrange the men. How many ways can I do that? How many ways can I arrange the men? 6 factorial. Now, I mean, this has a number. This represents a number. Whatever the calculator says when I say 6 times 5 times 4 times 3 times 2 times 1. But I don't care about the number. I care about how I get this. So I'll just leave it in this form, 6 factorial. I'm interested in the how, not the what is my final big number. I'm not done. What is my experiment? My experiment is arranging all the people. I've only done some of it. I've only arranged the men. So I need to follow that by step 2, which is arrange the woman. How many ways can I do that? Four factorial. So in total number of ways to arrange these people, step 1, followed by step 2. That's the basic principle of counting, saying that if I break my experiment up into smaller steps, so that it's step 1, followed by step 2, followed by however many I need to finish my experiment, then the total number of ways to complete my experiment is the product of the number of ways for each step. Everyone happy? 1, multiply, and all that. So see how every lecture we're adding something, but it also builds on what we did previously. So it's very important, especially for phase 1, to try to keep up with what we're doing in class. And if there's anything that's not clear at some point, make sure to resolve it by asking me or someone, asking before the next class, because we're building on it every time. Let's look at number 2. In how many ways can the letters A, B, C, D, E be arranged if I have some restriction? In the first one, I have no restriction. I can arrange them anyway. And B, I have a restriction where the letters A and B should be next to each other, and so on and so on. I'll do each one as it comes up. How many ways can I arrange these letters if there's no additional restriction? There are 5 of them, 5 factorial. They're all different, like people, 5 factorial. Everyone happy with that? Yes.
So if there's no restrictions, does that mean you can use one letter have to do each letter?
I have to arrange all of those 5 letters
So you can
in a
do the
row.
same letter twice.
There's only one A, only one B.
Okay.
It's like I have little Scrabble tiles. I need to make a row. How many different rows can I make? In B, now I want the A and the B next to each other. Now for a restriction like this, I have a very nice specific strategy that works often. What is my strategy? To make sure that every arrangement I count has the A and the B next to each other. I like to pretend I'm actually doing this. I have some Scrabble tiles. I have the 5 letters in front of me. And now I have to shuffle them in such a way that the A and the B are always next to each other. So one way is, let's glue them together. Let's glue A and B together. So now my letters are what? I have this super letter, A, B. I have a C, I have a D, and I have an E. So I only have 4 letters now. The A and the B are glued together, they move as one. And I do that because I need to satisfy my restriction that they're always next to each other. So glue them together. That way, I'll never have them away from each other. So I'm breaking up my experiment into smaller steps so that I'm guaranteed that I have the restriction satisfied. So step 1 is gluing them together. Glue A and B. Now how many ways can I arrange these letters?
4 factorial.
Let's say here I guess glue A and B and then arrange. He says 4 factorial, 5 factorial. Yeah.
Is it, if you glue them together, then is it always going to be A, B, or?
I glue them like that. Pretend you have Scrabble tiles. I glue them together in a certain order. Now that's the new time.
Okay, so what about when it's B, A? There's still together.
Well, I just have one step. I didn't say I was done. This is just one step on the way to looking at all the arrangements. I have more steps. Let's just check this step. Is everyone happy with this step? She looks at me and she's not happy. Just this step. All I'm doing is gluing, like that, A and then B, and now I'm arranging those 4 letters. Do you agree the number of ways to arrange these new letters? That's 4 factorial.
Want to see it later?
Huh? You don't like the 4 factorial?
Not yet. Maybe after.
But there's no.
No, I need you to like it right now. I have 1, 2, 3, 4 things. How many ways can I arrange them in a row? Yes.
There's no restriction on which order.
No, there's no restriction now. No. So 4 factorial. She's just not happy. Okay, so now you say, well, let me see, how do I know what I still have to do? And what often is a very good idea, and I still do that, is to sort of have a running example to see what have I done after step 1? What could I get? What do I still need to do before I'm done? Or am I done already? So give me an example of something that I can get after I've completed step 1. I pretend I have these tiles in front of me. Give me an example of what I can get. I can get many things. Many things. Give me one example.
A, B, C,
So the A, B letter she wants first, then a C.
D.
Oh, that's unoriginal, but okay. That is one thing I can get, sure. Now, what is upsetting her is I glued A and B together in this way. If I stop at step 1, have I covered the possibility B, A, C, D, E? Have I covered that arrangement? That's a valid arrangement. Have I done it if I stop at step 1? No, because I glued them in this way. So whenever I do shuffling these letters in the 4 factorial possibilities, it's always going to be A then B. I never have the possibility that they're the other way around. So what do I have to do in step 2 so that for every arrangement I get here, I also want to consider the one where they're the other way around. That way getting all the possible arrangements. So I have to arrange A and B essentially inside the super letter. Now I pretend I remove the glue. Now I can move them again. So I can have A and then B, but I can also have B and then A. How many ways can I arrange them inside this little square? 2 ways? Technically 2 factorial. That is equal to 2. This is equal to 2 times 1, which is equal to 2. But essentially I am arranging 2 things. And the factorial counts how many ways there are to do that. Everyone happy why I needed this step 2? You happier now?
Once I see the end part.
Okay, fair enough. Give me an example. So I'm sort of updating the example. At this point, I wasn't done. I had this glued letter, arranging this as if it was one thing. Now I unglue it, and I can shuffle them inside, and I get B, A, C, D, E. Maybe it stays the same. I have 2 choices for shuffling them inside the super letter. And that way I cover this possibility as well. And these are valid arrangements as well. So I needed another step. I couldn't stop at step 1. I needed that second step. So the total number of arrangements with this restriction that they have, well, I completed my experiment by doing step 1 in 4 factorial ways, and then I followed that by step 2, which can be completed in 2 factorial ways. So there's my answer. So I think if you want to see a final number, put it in the calculator, but it doesn't mean anything to me. This means something because I show how I'm constructing my answer, how I systematically thought my way through the problem. Any questions on this? Yes?
Does the order of the 4 and the 2 make a difference?
No, I mean, I can multiply numbers in any order. You can swap them. If for some reason your way of thinking has this step first and then that step, as long as it's one followed by the next, making up my arrangement, there's more than one way to do these things. But the basic principle of counting still says that whatever my step 1 was, that number of ways times the next one times the next one. If your thought process is slightly different, the end result is the same. Any other questions? So we're taking our time here because this is sort of where we cross over to actually now counting stuff and breaking it up into steps. All right. C. Now I sort of want the opposite restriction in that the B and D should not appear next to each other. Now I've just figured out how to put stuff next to each other, how to arrange with stuff next to each other. Now I want all the arrangements where the B and the D are not next to each other. Now I can try and do this directly, but not sure how simple it's going to be. If I put the B over here, for example, then I have 3 choices for the D. Sure, I can do that. pick a position for the D and then arrange the other letters, and so and in that way build my arrangement. But if the B was over here, then I only have two choices for the D. So it seems like they sort of depend on each other. Depending on where one letter is located, the other one's choices change, the number of choices. And whenever that happens, when there's sort of some dependency, it might be a slow process to count it directly. So I have to always check, do I look at a direct or an indirect approach to counting something? It's fine to check the direct approach, which is what we did in B, and that worked fine. Now in this one, where I want to separate stuff, it seems like there might be some different possibilities that I would have to consider separately, and it's not clear how easy that would be. So let's just check. We saw a strategy last time, and let's visualize that with a Venn diagram. And before I can use a Venn diagram, I have to give a name to a set. So let's say A is the set of arrangements that they're looking for, where the B and the D are not next to each other. They're separated from each other. Let's just give that a name. So in my Venn diagram, simple as it is, here in the rectangle I have all possible arrangements. The ones I calculated in A, they're all sitting in this rectangle. Now I'm looking for some of them. What is my restriction on the ones I'm interested in? I want all these arrangements to have the B and the D away from each other. So some of them will be in here, some arrangements will be out here when the B and the D are next to each other. And everything out here is called a complement. So let's just say again, what kind of arrangements are in a complement? If I have to say the word, it's good to not get caught up in the math. That's the whole point of phase one. But to be able to think about these things in simple English.
The set of arrangements where B and D are next to each other.
So here my restriction is B and D next to each other. So if A contains all the arrangements where the B and the D are separated, A complement has to be everything else. And everything else is where they're together. But I mean, it's good to be aware of it. What does this represent? Say it to myself, maybe write it down to make it more clear. Now we saw last time that if I don't want to count A directly, I can do it indirectly. Because hopefully one of these guys is easy to calculate. Either A is easy to calculate directly, or if it's not, then it seems, I'm not sure. Check A complement, maybe that's easier. I'll pick the easy one. This guy, the universal set, as we saw in 2A, is always easy. Without any restriction, how many arrangements are there in this rectangle? We saw there were 5 factorials. So if I have no restriction, that's always the easiest out of all of these things, when I have no restriction. Now I need to figure out, if I'm trying to use the indirect approach, what is this A complement? How many arrangements are outside here? And if I can find that, then I've done it. I've calculated A indirectly. But I've made it clear what a complement represents, what restriction it represents, and now I have the same thing I had in B, where I have two letters that I want next to each other. So let's count a complement, and I'll do that in 2 steps. Now, as we do these things more and more, we get more comfortable with them. You don't necessarily have to write out step 1, what am I doing, step 2, and then put it together. And we'll stop that after a while. But in the beginning, if you're not that sure about what you're doing, it feels a little new, it feels a little strange, I suggest right now, step 1, make it clear what my steps are, what am I doing at every step. We have so much time to do these things, it's better. And then I'm aware, I see, okay, step 1, I glue B and D together, and then I arrange everything. How many ways can I do that? How many ways can I arrange these new letters?
Or complement times 2 complement, or not complement,
I'm just doing step 1. This is all I'm doing. I'm gluing, I'm arranging, B is 1 letter, then I have an A, I have a C, and I have an E. That's all I'm doing. How many ways can I arrange them? Just 4 factorial. I have 4 of them, 4 factorial. So in the beginning, I'm separating the steps. I'm emphasizing each step on its own so that I can learn the way of thinking, the systematic way of thinking. Once I get comfortable with it, I just write it all at one go. But then I know what I'm actually doing. Step 2 is arrange the B and the D inside the super letter. I can do that in, well, there are 2 of them. Number of ways to arrange 2 things, 2 factorial. So how many ways are there in total? Step 1 followed by step 2. So it's the same as in part B. Let's just write here. What is this? 5 factorial minus 4 factorial 2 factorial. And again, I don't care about the final answer. You put this into your calculator. Your calculator has this factorial function built in. Most of them do. And I can find a number that means absolutely nothing. It's nice to see, oh, how much is this actually? But I leave it in this form to show that I understand, or to show how I constructed the solution. What was my way of thinking behind it? So if you stop there, that's all I'm looking for. If you write the big number that your calculator says, it's really just for your peace of mind. I'm not looking at it. I don't care. It's how we did the problem, not what the final number is. Any questions on this number 2? Yes?
Is there a way to figure out from that what all of the combinations are? Like, so you know that they...
You mean here?
Like, you know that it's... there's 5 factorial. There's that many possible combinations. But is there a way to figure out what each of those combinations are?
I'm just going to have to make a list. And there are 120 of them. This is 120. So the whole reason why we don't, and we just go to the question of how many, is because there's too many. We're just going to have to list them. I mean, these days you can just put it into a computer and it can shuffle all of them around until they give you the list of 120. But there's a big difference between knowing how many there are and knowing exactly what they are. Yeah, I'm just gonna have to make a list. It'll take a while, but you can do it. But if I had more letters, let's say I had 10 letters instead of just 5, then these numbers blow up very quickly, and I'll have thousands and thousands of possible arrangements. That's why I'm going to involve. Any other questions on number 2? Yes.
So you have to do both formats. You get the 4 factorial, the 2 factorial, and then figure out the 5 factorial. And then
But I'm trying to separate letters.
separate.
This is my original.
Okay.
My original issue was keeping 2 letters separate.
So the previous,
It's much easier to glue them together.
the previous answer, 4 factorial, 2 factorial on
2b.
Yeah, okay, so that's
That was the answer because my restriction was putting them together.
okay.
Now my restriction is keeping 2 letters away from each other. And I know, oh, okay, gluing them together is much easier. So if I take all those away from the total, what I have left is the set where they're all
And
separate.
so that's the final answer for C.
This one, yeah. So one of these 2 guys will always be simple. Well, relatively simple. And I pick whichever one is the easiest to count. If this guy isn't easy to count right away, I just think about the complement. Is this maybe easier? If it is, then just take it away from the total. Because this total is always easy to count. That's not the problem. The problem is which one of these do I prefer to look at? And putting stuff together is always easier. Yes.
So, in looking at the
Venn diagram.
Venn diagram, so what we were trying to find was what's in A.
This is just I'm just visualizing so I can see, make it feel better. I'm looking for how many are in this circle.
And that's the solution to when there's no B and P together.
I'm giving this a name. I'm saying, let's suppose in this circle
Okay.
are all the arrangements where the B and D are not together. Then what's out here? Where they are together. And that's much easier to count. So let's count how many there are in this whole rectangle. Count how many are on the outside here. Take it away. What I'm left with has to be the ones in this
Okay.
way. So indirectly, I'm doing it. Yeah.
You have to put brackets around your 4 factorial times 2 factorial.
No, I don't need any brackets here because the order of operations says multiplication happens first. But if you want to feel better, remembering that this is one thing, you can brackets it. Bed mass, multiplications first, brackets, exponents, and all that nonsense. Yes.
So when they're,
No.
what is 4 factorial, 2 factorial, they're right beside each other, does that mean they're
That means
multiplied?
multiply, yeah. I just don't put a little
Yeah.
dot there. There's no need for it.
Yeah, but it just means they're being multiplied.
Yeah.
Um,
This means multiply. What is 4 factorial? 24 times 2. So it's just 24 times 2. But I don't really care about the actual number. I leave it in this form to show where it comes from.
Times 4 factorial, 2 factorial, do the 8 factorial, just 8.
No. This is not equal to 8 factorial. The rule, you can't do that. You can't say A factorial times B factorial is A times B factorial. It doesn't work like that. The numbers, they grow too quickly. They grow too quickly, and this guy can't catch up. It's not the same. Yeah, they have to be separate. Yeah. But most calculators have this factorial built in, some sort of second function. Yes.
So the factorial is kind of another way of having an exponent then?
It doesn't behave the same as an
Not the
exponent.
same, yeah.
But it's the same.
Relationship.
The reason, where it comes from is essentially the same. Where does an exponent come from? It's because I multiply the same number over and over and over.
Yeah.
5 times 5 times 5. I don't want to write this. I write 5 to the whatever it is. So the motivation is the same.
Yeah.
The exponent comes from a shorter way of writing multiplication. This would be 5 times 4 times 3 times 3 times just want a shorter way to write that. But they don't behave the same in terms of rules and combining numbers. But sort of the motivation, both of their, the reasons for why they're used mainly, or originally, is to make the expressions more convenient to write. All right, so I'm taking my time here because we can. What time is it now? 10:02. Okay. So because all the next lectures rely so heavily on this factorial idea, this stepwise thinking, arranging, I'm taking my time today. We're not finishing this whole lecture. We're doing the rest. Some of it will roll over to next time, but we can do a little bit more.